So now we need to talk about complex eigenvalues and what happens if we have a system of differential equations and we end up with complex eigenvalues. Well, if we have complex eigenvalues, we know something about complex numbers. They always come in pairs, and they're called complex conjugates. So if we have something like a plus bi that is an eigenvalue, then that means that a minus bi is also going to be an eigenvalue. And there's a relationship between these and the eigenvectors, and what turns out that happens is that if a plus bi is an eigenvalue, and then we have this eigenvector, let's say the eigenvector is c plus di and then 1. Then for the complex conjugate, the eigenvector would be c minus di and 1. So notice that these will be complex conjugates of each other. So then if we come up with this and we know this eigenvalue, and we know this eigenvector, could we figure out what our x1 and x2 are going to be? And our x1 and x2 happen to be in this format. So notice that we are taking this eigenvector and we're splitting it into real and imaginary parts. The real part is called b1 and the imaginary part is called b2. And I want you to notice also that b1 and b2 kind of flip-flop positions here. And that actually comes out if we were to prove this. We would see why that would happen. So what I'm going to do now is look at an example. So let's look at this guy. And this is an initial value problem, which means we will be able to figure out what our C1 and C2 are going to be. So our first step is to figure out what the eigenvalues are going to be. So we need to find the determinant of a minus lambda I, and then set that guy equal to 0. So we know our A matrix. So if we take a minus lambda I, in this case, we are going to have 2 minus lambda, 8, negative 1, and negative 2 minus lambda. And we want to find the determinant of that matrix. So just to kind of review where that came from, our A matrix is 2, 8, negative 1, negative 2. And lambda I is going to be lambda 0, 0, lambda. So if I take A and I subtract I, we're going to end up with this guy. So if we find the determinant, this is a 2 by 2 matrix. So we're going to multiply these components together, subtract, and then multiply these components together. So now I'm going to simplify this. This is going to be negative 4 minus 2 lambda plus 2 lambda plus lambda squared plus 8. And we want to set this equal to 0. This is called the characteristic equation. Those cancel. So in this case, lambda equals plus and minus 2i. So now we need to find the associated eigenvector. So I'm going to use 2i. If we were to substitute 2i into this guy, our a minus lambda I, we're going to get 2 minus 2i, 8, negative 1, negative 2 minus 2i. And then we we have zeros here. Now we want to RREF this, put it in reduced row echelon form. So you have a few options. If you took linear algebra, you could do row reductions. That's a fun thing to do on a Tuesday night or Wednesday morning. If you wanted to, you could do substitution or elimination. I'm going to show you how to use technology to do this. So we are going to take this and we are going to substitute it into Wolfram Alpha. One thing you cannot do is plug this into a TI-83 or 84 in your matrix. Your matrix operations on the 83 and 84 does not have the ability to handle imaginary numbers inside of matrices. If you have a TI-89, I do believe it can handle that, but the 83s and 84s are not designed to do that. So we're on wolframalpha.com. And we want to do RREF. So notice when we type in RREF, it's giving you the format here. So you have to use the curly brackets. Those are called Victorian brackets around the entire matrix and then around each row individually. And we're separating each row with a comma and each entry in the row with a comma. So I'm going to go to my Victorian brackets. So that first one tells the program that I'm doing a matrix. Second one tells it this is the first row. My first entry is 2 minus 2i. My second entry is 8, and then I have a 0. And then I need to tell it this is the end of the first row. So curly bracket. And then a comma to separate. Second row is -1. -2 minus 2i. And 0. So that tells it it's the end of the second row. Then we have to tell it that's the end of the matrix. Hit go, or hit enter, equals. So this is a good way to double check you typed everything in correctly. And then when I do RREF, this is the output. So my RREF looked like this. So we're going to read this the same way we would read any matrix. This says x plus this number times y is equal to 0. That number just happens to be imaginary in this case. And then that row of zeros tells us we have a free variable. I'm going to let y be the free variable. So if we were to isolate x, we have that. So then what this means, I'm going to come down here, is that x is equal to -2 minus 2i times y. And y can be anything. So you literally can pick anything for y. I'm going to pick 1. So if I pick 1 for y, then when I substitute 1 in here, I get -2 minus 2i. Now we could have picked a -1. That would be fine also. You can pick any number. So this is going to give us real and imaginary parts. This is our B1, by the way. I'm just kidding. This is our K1. So then our B1 is the real components of our K1. So the real components are -2 and 1. B2 is the imaginary components. That's what it's defined to be in the theorem. So remember, that 1 can be written as 1 plus 0i. So the imaginary components are negative 2 and 1. Just kidding, negative 2 and 0. So we have our B1, we have our B2. Now I want to pause here for a minute, and I want to show you that we would get the complex conjugate of this eigenvector if we were to use the complex conjugate here. So if we used lambda equals negative 2i, I want to show you what would happen. So if we use negative 2i and we plugged that back into this matrix, we would have 2 minus negative 2i here and negative 2 minus negative 2i here. So we would have 2 plus 2i, 8 and 0, negative 1, 2 plus 2i, and then 0. So you can see the only thing that changed between this matrix and this one was what's going on down that main diagonal. And the only thing that really changed was that second entry for that item in each of those diagonal places. So let's do RREF on this so you can see that relationship come out of the problem. So we need to change this entry to a plus 2i and this entry to a plus 2i. Equals. So here's our double check. Make sure that you typed in the correct matrix. And then here's what we got. So we ended up with 1, 2 minus 2i, and 0. And then 0 is down here. So this says x is equal to negative 2 minus 2i times y. And y could be anything. So I'm going to distribute negative 2 plus 2i times y. So if we let y be 1, then our eigenvector would be negative 2 plus 2i and 1. So notice the difference between this guy and this guy. So do you see how they are complex conjugates of each other? That's always going to happen when we're dealing with complex numbers. You're always going to get those eigenvalues to be complex conjugates. You will always get the associated eigenvectors to be complex conjugates. So we have our B1, we have B2. We also know alpha and beta. We know alpha I think something got erased. So we know alpha is 0 and we know beta is 2. Remember, these are written in the form of alpha plus beta I. So we have these components. We have these components. We are ready to write that final solution. So So if we want to write that final solution, x1 is equal to, it's going to be b1 cosine of beta t minus b2 sine of beta t times e to the alpha t. So for us, our b1, the real components are negative 2 and 1. Cosine of 2t minus b2 sine of bt. All of that's multiplied by e to the alpha t. And then our x2 can be written as b2 cosine of beta t plus b1 sine of beta t. All of that's multiplied by e to the alpha t. So if we make our substitution here, our b2 is negative 2, 0 cosine of 2t plus b1, which is negative 2 and 1 sine of 2t, and that's multiplied by e to the 0t. Let me change this one. Alpha is 0 in this case, and e to the 0t is just 1, so these simplify just a little bit more. So there's our x2. Our x1, I'm going to simplify this. This is negative 2 and 1 cosine of 2t. I'm going to distribute that negative also just to clean it up. Sine of 2t. So we have x1, we have x2. The general solution would be c1 x1 plus c2 x2. So let's finish this problem. So let's write the general solution just to make this a little bit easier, because remember, this is an initial value problem and we need to solve for C1 and C2. So they gave us some information. We're going to make a substitution. They told us that x of 0 is equal to 2, negative 1. So if we make that substitution, this is going to be negative 2, 1. This is going to be cosine of 0 plus 2, 0 sine of 0 plus C2, negative 2, 0 cosine of 0 plus negative 2, 1 sine of 0. So I'm going to simplify some stuff. We know sine of 0 is 0, and we know cosine of 0 is 1. So we have C1 times negative 2, 1. plus C2 times negative 2, 0. This guy's a system of equations. Remember, this is a 2 by 1 matrix, same as those. So if we were to write this system out, that first line would say 2 is equal to negative 2C1 minus 2C2. The second line would say negative 1 is equal to C1 plus 0 C2. So right off the bat, we know C1 is equal to negative 1. We can find C2 by subbing that into that first equation. So 2 is equal to negative 2 times negative 1 minus 2C2. So this says 2 is equal to 2 minus 2C2, which means 0 is equal to C2. So if we substitute these back into that general solution up here, the 0 is going to go in for this guy, and that whole piece is going to be gone. So x is equal to negative 1 times x1. And I'm going to simplify this. This will go to both of those pieces. So we're going to have 2, 1 cosine of 2t plus negative 2, 0 sine of 2t. So we could leave it as this. Remember, this x is really the x vector. So x is equal to 2 cosine of 2t minus 2 sine of 2t. And y is equal to cosine of 2t plus 0 sine of 2t, which would just be a 0. So we could leave the answer in either one of these. We could do this top one, or we could do the bottom one. And there's our final answer. Oh, one thing. When I distribute that negative, don't forget to distribute to the denominator. This should be a negative 1, so this guy should be a negative cosine. There's our final answer.